Good afternoon to one and all here. On behalf of Department of ECE, CIT, and on my own behalf, I would like to invite our speaker of this session, Mr. Kanishkan, who is an alumni of our ECE department, CIT College, Coimbatore. He's a researcher at Eindhoven University of Technology in Electrical Engineering Department. His research activities include energy efficient hardware architectures, emerging memory technologies, and compiler design. Before joining TU, he served in ARM Limited at Cambridge, UK as SOC Performance Analysis and as a System Design Engineer in Tata Engineering R&D, India for 4 years. He is also a visiting researcher at Customized Parallel Computing Research Group of Tampa University. Kanishkan received his master's degree in embedded systems from the Eindhoven University of Technology and earned his bachelor degree from Coimbatore Institute of Technology. In his ongoing research, he is aiming to develop an architecture for a new computing paradigm, a memristor-based compute in memory designs, which aims to solve the memory wall bottlenecks of the conventional one-human architectures. Once again, I welcome you, Kanishkan, to present a topic on hardware platforms for deep learning in this time. Okay, thank you. Kanishkan, you can start your presentation.
Yeah, thanks a lot. It's a really detailed overview, but yeah, thank you very much. Yeah, so let me share the screen again. Right, you guys can see my screen, right?
Yes, it's visible.
Okay, perfect. So first of all, thanks a lot for the opportunity, and especially to the Pungadai ma'am and for the other organizing committee. Yeah. So as Cynthia ma'am mentioned, I was alumni of CIT, so I studied under them, 2014, 13, somewhere around there. And after that, yeah, I moved out of India, and then just doing my master's and then continuing on the research. So this is my first presentation in India, so I'm really happy that I'm doing it at my home university. So yeah, let's get started. And before I get started, I wanted to tell a few things. So first is, I have quite a lot of slides, but I don't want to present everything. And the second thing is, I wanted this presentation to be a little bit interactive. So it would be really nice, like if you guys have any questions, you can always interrupt me. And I'm sharing the full screen. So probably if you send something in the chat, I may not be able to see it. So in that case, you can just unmute and always ask it. And if you have questions, just ask it right away, because most of my slides are like a continuation. So if you miss something and if you hold it till the end, probably, it might be difficult to follow the rest of the slides. So is it clear? Okay, so the topics for today's presentation, today's talk is actually about the hardware platforms for deep learning. So before a quick intro about me, and I believe Cynthia ma'am already gave a really detailed one, so I just quickly summarize it. So I was actually from a farmer's family, so I from Pollachi, and then I did my diploma and bachelor's in India, and bachelor specifically in CIT. And then I was a system engineer in Tata Engineering R&D in Bangalore. And at the same time, I was also doing some course on IAC for innovative product design and developments. After that, I did my master's in TUE, and at the same time, I was also working in a lab called Sure Innovation Lab in TUE, which is basically like having a collaboration between academics and industry to implement the research knowledge in the industry. After my master's, I joined ARM, which is in UK, and I was working in the headquarters. So there I was mainly involved in the SOC level analysis and basically designing a mobile SOC for future systems. So probably the SOCs which comes in like 2 or 3 years might have a little bit of my work. So I'm really happy about that. Currently I'm a researcher in TUE. That's my main full-time job. And I'm also closely collaborating with Tampa University for other parts of the research, specifically on the FPGA and compiler designs. So I travel frequently to Tampa as well, and it's quite nice team there as well. And yeah, next, I don't know what happens, but yeah, we'll see. Okay, so a little bit about my team. So I work in electronic systems research group. So the research ES group is quite big. So inside that, we have a small group called PARS. So this is led by my supervisor, Henk Corporal. So he's actually one of the well-known figure in the computer architecture field. So he invented quite a lot of processors, and they are commercially used currently. So that is nice. And we also have like 5 other full-time professors and approximately 20 PhDs just under Henk. And yeah, quite some master students. So probably 1 to 3 master students per PhD. So yeah, I mean, parts like we are already like around 50 or something. In terms of research project, we have quite a lot of projects. So recently, my professor Henk, he started looking more into the deep learning side of things. So one of the current and the lot of people are working on energy efficient deep learning project. So that is basically like investigating like the deep learning models and what kind of hardware we need to do the deep learnings in energy efficient way. And also we work on a lot of signal processing related stuff. So the brainwave and brain sense or the projects which is about like wearables for the patient monitoring, specifically the EEG monitorings. I have a small demo later, so yeah, we will come back to that. So I'm specifically working on Mnemosine, which is basically designing a new non-one-human architecture for emerging technologies. REST, I mean, I will share the link, then you can have a look at it if you're interested. Okay, so before we get started, I just want a quick demo about like what kind of projects we are working on. And yeah, this is basically to just give a motivation about like why I am actually giving this talk and and what expertise we have in our group. Okay, let's see if this works. Oh, wait, I can't really. No. Okay, so this is basically a brain sense project. So what we have here is the small headset, which basically has an electrode which measures the brain activity. So the application we have here is basically an automatic typing. So basically, when you look at the screen on a specific key, the headset already recognizes your brain activity, and based on that, it can actually type in for you. So basically, you don't have to use a typewriter to type things. So this is actually a very interesting demo, and this project is in close collaboration with MindFX. So we are dealing with the hardware side of the things, and MindFX is dealing with the software and the other stuff, signal processing stuff. So as you can see in this one, basically what we do is we flicker each letter in a specific pattern. So when we look into some specific letter, then the brain has a corresponding activity. So we just try to detect that activity and then basically type it. So as you can see, like he is already doing well, and currently the rate is around 1 letter per 3 seconds or something, and we are trying to improve it. So here there are a lot of moving parts. The first is like we want this headset to be really wearable, so it's battery operated and stuff. So for this, we need on completely new designs. So so our team is specifically working on the hardware side of things, like making the new processors and how to make a chip which is like really energy efficient, and also deep learning side on the bed. And MindFX, it's mostly on the signal processing and application side. Right. So coming back to our slide, so this is just one project. So we have a few other projects which is similar to this. So the main goal for my talk is about like implementation view of the deep learning. So as I mentioned before, like I dropped in few sessions like yesterday and day before yesterday, and I noticed that most of the sessions are like really high level, and they already gave a good view on the deep learning and how to use them on the signal processing, I believe. So in this talk, I want to focus on like, okay, so if you have a deep learning model and if you have an application in mind, then how do we implement them in an energy efficient way? So I think in one of the talk they were talking about like if you put deep learning on GPUs, they are much faster than CPUs. So in this talk, after this talk, I would like to give an overview of literally, kind of most general platforms, and you would be able to reason why GPU is faster. That's my main goal. And the challenges, like, okay, why we had to look into the side, like, okay, what are the problems? Like, why can't we just let the compiler do the job? And the second one is, again, as I mentioned, it's about energy efficiency again. Okay, and most important thing is, I want to learn it from each other. So basically, like, we are working more on the hardware side of things, and you guys are experts in the signal processing and related areas. So it would be really nice to kind of have an just exchange knowledge so that we both can benefit. And if you have any feedbacks or anything, you are always welcome to contact me in email or LinkedIn or anything. That should be fine. Okay, so before we dive in, do you guys have any questions at this point? Oh, yeah, okay, totally. I have to see the chat as well, I think. Okay, so no questions? Okay, so, and am I speaking too fast? If I do, please do stop me. Yes, just let me know. I will change the phrase. So, okay, so let's continue. This is the outline for my talk. So first, a little bit motivation about like why we have to look into energy efficiency, because I mentioned quite a lot about energy efficiency, but what does it really mean and why we need to look into them. And the second one is like, the deep learning, like what are the design challenges and what are the implementation challenges in the deep learning networks. And then we move a little bit on to the actual topic, which is like, okay, so if these are the challenges, then how do we choose the hardware platforms and how can we implement them in more optimal way? And finally, we will have a little bit look in, kind of an outlook into an research topic, which is like, okay, so the convention, so this is actually one of the research topic which I am actually working on. So this is a bit interesting. So basically, we kind of redefine the entire traditional system, and it might be interesting to see like how we can use the analog computations to make this neural network more efficient. And finally, just a quick recap, and let's see what happens. And this one is quite a long presentation, 1.5 hours. So I understand it's already an afternoon hour. So you guys might be tired already. So after like 30 minutes or 40 minutes, we will take a 5 minutes break because of Corona. I have to switch room every 1 hour. So that also gives me time to move to the next room and probably get some coffee. Hope that is not a problem. Okay, so motivation, as you can see, deep learning is used literally everywhere. So it starts from the normal image recognition to advanced automated car drivings. So it's getting more popular nowadays. So the industry also trying to adapt to this trend. So if you look into the recent product release of any major companies like Apple or Intel, they have more machine learning and the neural network terms compared to any other terms, because like it's a quite hot topic, and the challenges on this domain is quite a lot, and especially if it is on battery operated devices. So before we proceed further, I just want to have a quick recap of like what is artificial intelligence and what is deep learning. So some people use this term interchangeably, but the ideal meaning is, at least in my presentation, I try to keep this abstraction. So the artificial intelligence is to convey the intelligence to machines. So it can be a simple program or it can be anything. So even if you write a small program which basically checks something and does something, it's still an intelligence. So we can call it as an artificial intelligence. We can have a lot of debate about it, but that's my point of view. And the machine learning is basically like data-driven prediction. So basically, the machine can learn the behavior itself. That's the machine learning part. And the deep learning is actually a subset of machine learning, where we use deep neural networks to do a machine learning. Okay, so one of the popular examples of the popular use case for the deep learning is the image classification. So, which is basically like we pass in some input, and the classifier basically categorizes these images based on the output classes. So in this case, I just took a really small example, which takes input image and says like whether it is a human or not. So this slide is actually from my professor. So don't blame me. So basically, if you pass on small image, basically this classifies yes or no. So I don't want to discuss the results here. So let's move on. Okay, so we can able to classify with the deep learning networks, but how good are they currently? So that's a really important question, right? So the image net challenge, which is basically tries to do that. So what it does is it takes like quite a lot of image sets and try to do the classification and see the performance. So basically, it takes like 10 million images and tries to classify them into 1,000 classes. So for example, some of the examples of the classes are like dog, cat, or something. So if you pass some image from this one and try to get the output. So the output they categorize based on how many false positives they have and proper positives, and try to say, okay, this network is better than this one. Okay, in terms of performance, in this graph, kind of, it's a bit old, but still gives a good overview. So as you can see, in the x-axis, we have an year, and in the y-axis, we have an top 5% error. I hope everyone knows what it is. So when in 2010, as you can see, so basically the y-axis, like lower is better, which means like if you have less false positives, then it's good, right? So in that sense, in 2013, the network were not that great. And in 2012, well, kind of deep learning become really popular. And as you can see, there is a huge shift there. And after that, like every year, it was actually the accuracies actually keep going on. So as you can see, in 2015, it even surpasses the human, which is like 5%, I believe. And still it's improving. And after 2017, it's not going down that much, but still there is a lot of improvement over there. Okay, so okay, that is good, right? But as in the semiconductor field, you already know this term, I believe, so which is like there is no free lunch. So this holds for DNN as well. So if you want to have a really good accuracy, the computation cost is really high. So in this graph, basically, I try to, basically this is taken from the Nature publication, like 2 years back. And in the x-axis, we have an accuracy, which is lower means good. And in the y-axis, we have a number of operations, which is like the compute intensity. So as you can see, if you want accuracy, the computation is massive. And this is already in 10 power 9, which is like giga operations. So if you want one really, really good, so you need to go above 10 giga operations per image, basically. But normally, if you have a video, you will have like around 20 frames to 60 frames. So which means like you have to multiply this number into 20 or 50, which is crazy, right? So if you run it in CPU or GPU, it takes forever. Okay, so this is one side of the problem. On the second side is we want to use the deep learning in different applications. So for example, we want to use it in medical fields, especially in the wearable and stuff. And on the other hand, we have to, we might have a lot of compute resources. For example, Google, they have huge clouds, so they don't have any, well, they still have a problem, but they have a lot of resources, so they can implement more accurate networks. So if we look into high level, so we want to implement the networks in edge and as well as high performance cloud, and in between we have different other things. So in the edge node, the energy budget is quite limited. So the computation power is also very limited, as you guys know. And then high performance cloud, we have more compute power. So when we want to have a more accurate network on the edge node, then it's a problem. Like we need to think about a lot. Okay, so but from the deep learning perspective, we can classify the workloads into mainly 3 types. The one is inference, which is basically giving an input and predicting an output. And the second one is training, so which basically like letting the machine to program itself. So we will come back to the training part a little bit later. And the meta learning is basically it's a kind of derived version of training, but it's kind of hybrid, I would say. In these workloads, training is more compute intensive part. So that is because like you have to train the network with a lot of inputs, which takes a lot of time and computation power. On the other hand, in terms of compute platform, we can mainly classify into 2 things. One is high performance computing, and the second one is embedded system. The high performance computing means like basically like any, we can classify it as any hardware which is connected to power source, that we don't have a lot of restrictions on the energies. And on the other hand, we have embedded system, which is basically battery operated or like has a limited compute resources. So in terms of hardwares, so based on the combination, we have wide variety of hardwares available in the market. So the CPUs are very general ones, as you guys know, Intel, AMD, and quite a lot of other stuff. And the GPUs also, quite popular nowadays, especially the AMD and NVIDIA stuff. And there are other things like FPGA, DSP, ASIC, and ASIPs. So ASIP stands for Application Specific Instruction Processor. That is also a really interesting field, but it's well, that requires a lot of hardware side of knowledge. So I'm not actually talking a lot about the ASICs in this presentation. So if you're interested, you can of course contact me. Okay, so in this one, we kind of categorize this different processor classes into flexibility versus energy efficiency term. So energy efficiency means like how much computation we can perform in a given fixed energy budget. So the energy efficiency of CPU is a bit low and ASIC is quite high because ASICs are designed for specific application or specific neural network. And in terms of flexibility, yeah, the CPUs has more flexibility because you can run DNN and at the same time you can run your own any program like even games or something. So basically you can run any application on CPU, but if you design ASIC for DNN, you can only run that particular DNN. So if you want to change something, then it doesn't have much flexibility. So based on this categories, we can select the hardware, but yeah, again, we will come back to this bit later as well. Okay, right. So in this one, we will be specifically looking into the hardware side of things, like how to choose the platform and stuff. So in terms of, if you look into energy efficiency perspective, there are other research domains as well. So one of the most common and popular ones are inference and learning principle, which means like you kind of design your own deep learning network and for your specific application. So if you customize your network, then you can always get a good accuracy. And there are a lot of other learning principles as well to save time and save computations and stuff. So one of the things is network architecture search, which is basically like having small DNNs to kind of model a big DNNs. So and the second one is improving the network efficiency itself. So in terms of improving network efficiency, there are multiple research domains, but in this one I just listed only 3 popular ones. The first one is network pruning. So let's say if you have a really large network and if some of the weights are not really contributing much to the output, we can just remove them, right? So if we do remove them, then the network gets simplified and the computation will get reduced. And the second one, if you can do a same operation or same inference with the smaller network, then we don't really have to use a bigger network, and we can actually split a bigger network into smaller ones and try to have it kind of completely separated. That actually saves a lot on the training time. And the third one is quantization. So like most of the systems now are 32 or 64-bit. But for deep learning, we don't really need 32-bit or 64-bit resolution. So we can always go with like 16, 8, or even 4-bit resolutions. So by reducing the weight size, then we can actually save a lot of computations with the SAMD and stuff. So we will come back to this as well again a bit later. And the other completely different domain is loop transformation. So which is basically like if you have a deep learning network, then in the compiler, you can do a lot of optimizations. Like the deep learning networks are basically like a nested for loop of 7 levels. So if the compiler is really, really smart, then you can actually do a lot of optimization in the compiler itself. There is actually a really nice trick as well. So this is one of the things we were looking into as well. So if we have time, we will have a quick overview as well. Okay, so that's my motivation for why we need to look into the deep learning, or well, the energy efficiency side of the deep learning and the hardware stuff. Okay, any questions at this point? Okay, oh, sorry, the screen is not visible? Hello? Hello, can you hear me? Okay, so maybe someone unmuted because I am not really sure when it stopped. So
visible,
okay,
sir.
But yeah, thanks a lot. But at which slide it actually stopped?
Underwear platform for DNN.
Oh, this one, right?
Yes, sir. Yes, sir.
Okay, perfect. Right. So, okay. So I will just have a quick summary. So I am again not sure like when it stopped. So okay. So basically, we have a different workloads, and each workload has a different compute intensity. So on the other hand, we have compute platforms which are either high performance or embedded systems. So in this combination, we have several hardware platforms available to us, which starts from CPU to ASICs. The CPUs are less flexible because actually it has more flexibility because we can run any programs. But if you design ASIC, then the flexibility is quite low. So we can only run that particular application. So in terms of energy efficiency, the ASICs is high and CPU. So there is always a trade-off. So this is what I am actually focusing on the rest of the presentation, like why do they have a different energy efficiency and flexibility. Okay, so other research fields are similar to improving energy efficiency or inference and learning principle, which means coming up with a new network model and learning principle to do the same kind of inference in a more accurate or more energy efficient way. And the second one is improving network efficiency, which is basically like if you have a network, then some of the computations might not really contribute to the final output. So in that case, we can actually get rid of some nodes and save some computations. And the second one is the compact network architecture, which is like instead of having a really large network, we can just split the network into small networks and have them pipelined. So this saves a lot in the computation time because like if you have a large network, training them takes a lot of time and effort. And if you have a small one, it's a bit easy to train. And the last one is quantization, which is basically like, most of the computers are either 32-bit or 64-bit. But as you can see in the figure on the left, so you basically have a data path which starts from high level to low level. So in this case, we are doing 4 or 5 multiplications. So if you have 32-bit data, then every time you do a multiplication, then you are overflowing with the data bits. So one of the way to do it is like you can reduce the precision, which is like instead of 32-bit or 64-bit, you can come to 8 or even 4. Actually, nowadays we are even designing a 1-bit network. So if you have 1-bit network, you are basically doing an XOR, which is like really energy efficient compared to the multiplication. Other side of the completely different domain to look into the energy efficiency is the compiler side. So basically, like the deep learnings are literally implemented by nested for loops. So if you have a super duper compiler, then the compiler can already do quite a lot of stuff. But most of the current compiler cannot really handle it. So if we can implement some optimizations in the compiler, which can actually do that, then we can improve a software, the overall energy efficiency a lot. So this is also one of the research fields I'm looking into. So there are quite a lot of things. Okay, so this is where I stopped before we cut off. So I was asking, like, is there any questions so far? Okay, I am a bit not sure that, like, probably am I going fast or like, is everything fine? Because I normally get quite a lot of questions, so I haven't heard anything, so I'm not really sure. Pumade ma'am or someone else have? Okay, so let's continue. And again, if you have anything, just interrupt me. Okay, so the next is, so before we go into the hardware platforms, I just want to give a quick overview about the deep neural network and its challenges. So the deep neural networks are basically, neural networks in general are inspired by our brains. So basically we have a cell body which actually receives an impulse or action from a different cells. So as you can see here, we have a really big cell body which is connected to like 4 or 6 other cells. So whenever it receives an impulse, it gets activated, and the action pulse are sent through axon. So as you can see, in this case, the axon is again divided into 2, and each axon will have a different weight. So basically, whatever the impulse we have is weighted some over these branches, and it gets delivered to the next cell. And again, the same for the lower one. So how these weights are actually programmable. So that is basically our memory. So let's say if you are looking at the dog and the dog has some specific weight, so you can actually, your neuron will have some specific weight. And when you see a dog, then you get a really high impulse on one neuron compared to other one. And yeah, the next cell gets activated and it just propagates. So in neural network, we basically try to model this exactly same. So yeah, as you can see here, the inputs are from axon, right, for a cell. So this is basically an x0.
Hello.
Yeah.
Hello. Sorry, I'm interrupting you. But screen is not visible, sir.
Oh. Okay.
Sir, I think it is visible. Nitin, sir,
Okay.
I guess you need to
Yes, sir.
unpin your screen, and then it will be visible because it is visible all the time.
Okay, it is visible. So
Okay, I check my side.
Yeah.
okay. So I mean, which slide is it in? 33, right?
Yes, sir. We are here.
Okay, perfect. Right. Okay.
Okay,
Sorry about this.
thanks.
I
Sorry.
think there is some network issue or something. Yeah. Okay. Let's continue. So this in this case, we are modeling input as an x parameter, which is basically the impulse from external cell. So this is x0, and as I said, axon has a specific weights, right? So for this cell, you have like 6 axons coming in. So we will have 6 weights for each axon, and this is going into the cell body. And when the cell receives a lot of impulse, and it has some activation function. So once it receives the expected number of pulse at specific magnitude, it triggers, which means it produces a pulse on the output. So that is actually going as an output action to other cells. So note that this is just a single cell. So similarly, we have quite a lot of cells. So if you have like 10 cells, which means 10 cells in sequence, then that's kind of already a deep neural network, because like we will have 10 layers. Right, so this is quite basic, and you guys already know it, so just want to recap it. So, okay, how do we model it in the software is a different story. So let's say you have an input parameter, which is x0 to x3. So in this case, we just took 3 inputs, and the weights are basically like on the edges of this connections, and y is basically an cell. So in this case, we have like 4 cells. And the input we pass from x0 are passed to all 4 cells. And yeah, our final output is also collected from all 4 cells. So this network, we kind of call it as a fully connected network, because like each input and outputs depends on each cell. Well, cell body, basically. So in the deep neural, so the only thing what we are doing is we are kind of programming this weights. Well, not really programming, and we are kind of learning this weights. So if you pass some inputs and if you learn this weights, then you can do an inference with it. In terms of programming, it basically boils down to this really small equation. So basically, if you have an input, you will multiply it with the weight on the particular edge, and then you sum it on your y0. So for example, here y0 would be x0.w0 and x1.w1, something like that. Okay, hope it is clear, and if not, just let me know. We can do, yeah, I can go a bit more. Yeah, as you can see here, we are getting an input, and this is actually passed to all these cells. So which means that we can execute, well, basically we can kind of execute all the cells and compute the cells output, sorry. We can compute the activation of all the cells in parallel, right? So that means that we have quite a lot of parallelism. So this we can exploit with our hardware or yeah, any other things. Okay, so as we discussed before, I mentioned that in the workload we have 2 types. One is the inference, and the second one is the training phase. So inference is just like computing with the deep neural networks, and the training phase is basically like learning the weights. So in this case, yeah, we have, as I said, we have to learn this weight, right? So that's the training phase. Okay, so how does it really work? In the training, so in the inference, let's start with the inference phase, because that is much easier to interpret and understand. So in the inference phase, basically you pass an input, and the input here, like 3 dots, are basically on each pixel or something like that. And the input pixels are passed to each cell body, and each cell body produces an output impulse. And finally, we get an final output here. So this one has like, yeah, just 2, but yeah, I mean, this is not really matching one. But basically what we finally get is the probability of the input belong to the particular class. So in this case, like we have like 6 classes. So there should be 6 red boxes, but that's not that's my mistake. So as you can see here, when we pass a dog input, we get a high probability for dog, which means like for the first class, and for the remaining class, we have a low probabilities. So from the probabilities, you can already say that, okay, this is dog. That's what the inference really means. Okay, so then what about the training? So in the training also, we do inference. It might be sounds tricky, but that is basically the case. So basically what we do is we pass some input image and we try to classify the output. But for in the training phase, for the input image, we know the results already. So for example, when you pass a dog, you know we are going to pass the dog. So in the output, when you check the probabilities, you are checking whether it is detecting as a dog or not. If it detects as a dog, then we are fine. We can just leave it or update the weight a little bit. If it is not, we can just calculate the error. And based on the error, we can just kind of tune the weights. So what weights we should tune depends on your algorithm, because like if you can even have a really complex model to kind of update the weights, or you can have a really simplistic model, like just randomly change some weights and see the results. So it's completely up to the training algorithm. So as you can see here in the training phase, we had to pass a lot of images to have weights which can classify these images. So which means like we are doing a repeated inference over and over. So that's why the computation on the training phase is really, really high compared to the inference stage. So normally what people do is they train the network, or they learn this weight on the high performance cloud with the servers and stuff. And once they know the weights, they can just transfer these weights to the embedded systems, which means like in embedded device, we can only do inference because of the energy budget and stuff. Training the network on embedded system is also possible, but it's like, yeah, it's not practical. Okay, so this is nice, but how does the practical DUPL neural network looks like is, you can see it from this figure. So basically the input and outputs are, the input is an image and output is classes. So input doesn't need to be image. It can be a signal from, for example, EEG source or something, or it can be anything. So in the network architecture itself, we have several layers of the network. So most general ones are the convolution layer and fully connected layer. So in a typical high accurate deep neural network, we will have like 5 to 1,000 layers of convolution, and at the end we might have fully connected layer or something similar. So basically we get an input, we calculate output of one layer, and we just pass it to the next layer and it goes on. So this is straightforward. But the interesting thing here is that around 90% of the computations are actually from this convolution layer. So as you can see just from the numbers, if we have more layers, then the computation is quite large. So let's have a little bit more look into where these computations are coming from. Okay, so you guys already know the convolution. So basically, if we have an input image and we have a weight, which is of size Rs, and the input of HS. So if you want to do a convolution with a moving window of 1, then you just take an first weight and then just overlap it on the first 0,0 position and try to compute the output. And for the next question, we just do one. So the another thing is like when you do this computation, you are multiplying R cross S with this one. So which means like you are doing R cross S multiply and accumulate operations. And when we do shift 1, then we again like compute the same thing. So which means basically we just move the window and try to calculate it. Similarly for the rest, so basically if you move the window on the side and as well as up down, then you will calculate the entire output. So in terms of the max, it's multiplied by, so I assume that the moving window size is 1, so we get this many MAC operations. As you can see, it's already quite a lot, but the convolution layer is not just this simple. So generally, you will have multiple input feature maps, because like if you're capturing an image, you will have an RGB, right? So if RGB are different channels, so each channel will have its own image and stuff. So to calculate the final output, you need to perform the same operation over different channels. So to do that, we will have a same kind of weight. So that's fine. But what happens is this entire computations are multiplied by the channel size again. But again, this is not that simple. So sometimes you may have to calculate different output classes, right? So which means that you will have a different weights for each output feature map. So for example, in the previous figure, we had like 5 classes, which is like categorizing dog, cat, and few other stuffs, right? So if you have like 5, then you will have 5 output feature maps. And yeah, again, there will be an activation, but still it's 5. So as you can see, again, the entire computation is multiplied by m. What m is basically the output feature map size. So this is actually quite a lot of computation. So if doing that is not really that easy, but yeah, another thing is, like as I mentioned, like in the video, you will get more than 1 frame per second, right? So which means like you will have multiple inputs. And if you want to perform everything in parallel, then you duplicate your weights as well. So basically, you will again multiply this entire combination with n. So as you can see, this is really, really massive computations, right? Okay, so this is one part. And the second thing is at the final stage, we also have a fully connected layer, right? So the fully connected layer is the one which we saw in the first example. That is basically a cell body connects to all the axons. So fully connected layers are quite straightforward, but so basically if you have an input feature map, the weights are exactly same as the size of the input feature map. So in this case, if it is RS, then we just do duplicate. So basically what we do is we take this weight and multiply just once, and then we produce one output. So what it really means is that we can just do an matrix multiplication, right? Because it's just one, well, it's just 1 cross 1 multiplication. And if you flatten and stuff, yeah, you get as a matrix multiplication output. Yeah, there is more to the transformation part, but we don't have to go in. So in summary, the fully connected layer are also compute intensive. Okay, so is that all we have in the deep neural networks? No, not really. So we also have a few other things. So in each layer, we also have some nonlinear functions. So when we do a convolution, then what happens is like you are getting a, let's say if you're having 5 inputs, you are passing it to a convolution layer, then it gets multiplied to scale to many inputs. And if we have like 1,000 layers, and every time if the input gets scaled, then at the end, yeah, we will end up with a lot of inputs. So what we normally do is after each stage, we try to kind of reduce the weights by just selecting the weights which are selecting the output which are interesting to us. So to do that, we have quite some functions, and yeah, as we've seen in the first figure, like each cell body has an activation function, right? So the activation function basically combines all the input and produces just one input. So the activation function is generally, yeah, it can be linear or non-linear, but non-linear function seems to work much better than the linear ones. And yeah, similarly in the fully connected layer, so we should have something to check for the probability and select the one which has maximum probability. Okay, so this one gives a good overview of a practical DNN structure. Okay, so I hope the connection wasn't that bad, Ed. So, okay, any questions at this point? Yeah, okay, sorry. Right. Okay, let's continue again. Okay, so if you look into the practical view of things, so as I said, like at the end, the fully connected layer is just a matrix multiplication, and the convolution is just moving window, right? So if we model this practical DNN structure into an C program in a more generic way, we will end up with a nested for loop of 7 layers, 7 levels. So basically, we iterate from the image size to feature maps and the weight size. It's quite a lot of. As you can see, the main core computation is really, really simple. We just multiply 2 things and then add it with the accumulated with 1 other variable. So it's like just a multiply and accumulate operation. So this is really nice, but yeah, implementing them is actually a bit hard. Okay, so we know that, yeah, so the computations are quite intensive, but how intensive they are. So in here, basically, we compare the different networks and their compute intensity. So as you can see here, I mean, the most important things are highlighted. So the number of convolution layers. So if you go deeper, the accuracy goes higher. Well, basically, the lower error means more accuracy. And the number of weights also gradually grows, and the number of operations also gradually grows. So as I highlighted in the yellow lines, it has to store like 25.5 megabytes of data if we assume each weight is like 1 byte, but it's not the case normally. and we are performing like 3.9 giga operations per second just for one frame, which is kind of crazy. So, and if you want a real-time performance, you need like around 100 giga flops per second, something like that. So that is the level of complexity we are currently talking about for the DNN networks in practice. Okay, so I hope there is no questions, so we can continue with another one as well, I think. Okay, let me see if I have crossed the time. Okay, now we can go for another 10 minutes or something. Okay, so the generic hardware platforms, right? So the generic hardware platform here means that the hardware platforms which are commercially used and are available to everyone, specifically for the general public. So the general platforms in this case is basically the CPU, GPU, and DSP maybe, because for programming this, you don't really need an expertise knowledge. We can just program it, we can just let the compiler to it. Okay, but that's quite nice and easy to use, but what are the downsides? We will look into them one by one and see what happens. Okay, so the CPU. So in this figure, we basically, it's actually taken from a different paper. It's quite old, but still it holds. So in the x-axis, we basically have an year, and in the y-axis, we have a performance metric. So so important thing here is the single thread performance, which basically means that if you have one single core, then what is its peak performance? So as you can see, because of the technology scaling, the single core performance was keep on rising until 2004 or something. And in 2004, DNAS scaling happens. So DNAS scaling in the sense like, okay, so basically what transistor scaling is basically like reducing the size of the transistor. So if you reduce the size of the transistor, the area goes down. If the area goes down, then delay also goes down. And frequency goes up. But to keep the electric field constant, you need to reduce the voltage as well. But after a certain point, you can't really reduce the voltage because the transistor cutoff voltage is like 0.35 or 0.7 or something. So that's the main reason the single thread performance stopped somewhere here. But interestingly, the multi-core kicked in around in this same time. So in the multi-core, in the same chip, we have multiple cores. So currently, I think around 632 cores are quite common. So if you have more cores, then we still get more performance. So which is good, right? So basically, if you see the final performance, so if you have more cores, like around 10 or 20 cores, the single thread performance is also increasing. So if you multiply this factor, the overall performance we get is quite a lot. So that is actually nice, but why it is behaving so badly for DNN is because of this reason. Okay, we'll come back to this slide again. Okay, because of this reason. So the CPUs are generally designed for general purpose applications. Like basically we want to run any applications on the CPUs. So what we do is like we have to maintain the generality, we put a lot of hardwares to support everything. So that has a downside. So that means that like the control overhead on the CPUs are quite high. The control overhead here in the sense like the instructions we issue or the program we send it to the processor. And also in the cache in the CPUs we have caches which is tuned for general purpose applications. But I mean for deep learning networks, the cache behavior is quite different. So we can't really change the hardware stuff once in the CPUs. So that kind of gives a downside as well. So in summary, like around 50 or 60% of the power is spent on the control overhead on the CPUs. And on the core computation here, in the sense the number of MAC operations, we can consider as MAC operations. So then we are just spending only 40% on the real computations. The rest are just control overheads. So that's why even though the peak performance is improving, it's not that efficient for the deep learning. Okay, but how far we can reach? So in this graph, we basically have a technology scaling on the x-axis and the computation efficiency on the right. So as you can see, the x-axis, the lower part of the figure on the left are basically the CPUs. The CPUs are basically having a less computation efficiency. So compute efficiency means the number of operations we can perform per watt. So the reason is again same, because of the control overhead. On the in between, we have something like an GPUs, which is GTX 800 and other stuff. So in this one, basically what happens is, the GPUs are a little bit better than CPUs, but still the energy efficiency is quite low because of the same reason, which is the control overhead. So at the higher end, we have an DSPs. So DSPs are tuned for specific domain. So in that sense, yeah, they are actually a bit better than the normal ones. But what is the maximum we can achieve? So the really energy efficient ones at the market currently are the Google TPUs. Anyone heard of them? Yeah, probably most of them. So TPU stands for Tensor Processing Unit. So this is commercially available, and you can just use it from the Google Cloud. So if you compare the TPU energy efficiency with the CPU, it's almost like 200x away from the CPUs. So because like the CPUs are very generic and stuff. So yeah, when we look into the TPU in a couple of slides, we will get a good idea about why it's much better than CPUs. Okay, so in summary, the CPUs are not efficient. Okay, so then what about the DSPs? Okay, so this one is the recent, it's not recent, like 1 year back, they released this processor. So as I mentioned before, like many of the vendors are adapting their architecture for supporting deep learning networks. So in CPUs are not really energy efficient, right? So to make it a little bit better for deep learning, they started adding very DNN specific modules in their CPU itself. So this is actually i9, I think. So yeah, we already have like 2 neural network engines, which basically performs the vector operations. Yeah, if you're interested in specific stuff, again, you can contact me. And the second one we have is the DSPs. So the DSPs are kind of optimized for specific domain, right? So they have less control overhead compared to the CPUs. So as you can see here, the amount of computation, the core computation we perform is actually quite a lot compared to the control overhead. So in terms of energy efficiency, they are definitely better because of several reasons. So I mean, I don't think we have to go a bit more, but they are quite, specific to a given application. Yeah, we will do it in the next slide, I guess. Okay, so in the DSPs, as you can see in the left, you have like around 70% on the computation and just 40% on the control overhead, which is reverse than the CPUs. So they are better. Okay, so this is actually one of the DSP which is used for deep learning. So here we have, compared to CPUs, we have quite a lot of processing clusters. So in each cluster, we have a different processing units as well. So as you can see here, we have so this processing units and sequencer and stuff are to perform the general computations. And alongside the general computations, we also have a neural engines. So the neural engines, basically what it does is it performs the vector matrix multiplication. So the convolution array are generally just vector matrix multiplications. So instead of just doing each operation one by one, you can do matrix level operations in the just single shot. And as I said, like we need a lot of memory and to store the weights and stuff. So they have like different memory hierarchies to support maximum reuse and capacity. Yeah, so in addition to that, they also have an optional custom AI engine, so which is again the convolution array, but with some specific things. And as you can see here, in addition to the general matrix multiplication, they also have a specialized unit like the linear and nonlinear activation functions and stuff. So this dedicated implementation actually helps a lot in the DNN performance. So this is just one cluster. So they normally have quite a lot of clusters and they have an application and stuff. So as you can see, like this is already having a massive compute power. So that's why they are very efficient for the DNNs compared to CPU. Okay, so there were other few examples as well, but for now it should be fine again. Okay, so the most common ones currently used for training the deep learning networks are GPUs. So if we look into the SIMDs, which are available in the DSPs and CPUs, so basically what we do is we have a different, basically we issue one instruction and we compute all the input in just single shot. So in scalar version, what we do is for performing add of A plus B, we use one instruction. But in the SIMD, you can do an array of additions, like you can do 4 adds in just single instruction. That's what SIMD really means, single instruction, multiple data. So in this case, like we have a 4 wide SIMD, which means like it can perform 4 operations in just single cycle. And yeah, we just read them right from the vector load store units. The GPUs are quite different because they don't really share the instructions. So they have similar kind of setup, which is like they have an compute. I mean, each pipeline has its dedicated load store unit compared to SIMD. So on each compute unit executes its own thread. So, and we have like thousands of cores in the GPU, so they can execute like thousands of threads in the same time. So they are, in terms of the programming model, they are quite different. So the SIMD is different one, and GPU uses single instruction multiple thread model, which is called as SIMT. So the main another difference is the shared memory. So in GPUs, each compute block has its dedicated, maybe kind of shared memory thread blocks. But in the SIMD, we always go through the global memory and read it back, which kind of creates a bit inefficiency. So if we look into the exact execution model, so what we do is we kind of create a threads, well, thousands of them, and assign each thread to each core. So basically, threads inside a single block, which is called SM blocks, and execute everything in parallel. So if you say execute add, basically add is executed on all 4 threads, and the final result is showed in the shared memory. And in the next cycle, you can read this memory again, and then do the new operations. So this is just one core, and I hope it's clear. And if we look into the Fermi GPU, which was like really old one on 2019. So we just they use the naming convention SM. I don't really remember the exact acronym, but yeah. So each green box is an execution unit. So as you can see here, we have like around 1632, like 16, right? Yeah, 16 SMs, and each one will have like 32 units. Yeah, I think I should have, we each one will have like 32 cores. Something. Yeah, so each SM has a 32 cores, which means like 16 cross 32 threads in parallel, which is crazy, right? And this is, again, it was on 2019, so it offers like massive compute powers. And if you look into the bit recent one, this is actually NVIDIA Volta, a bit popular one, and it's released in 2017. So this one, as you can already see, they increased the number of clusters a lot. And they also added a special support for the deep learning. So bit closer look. So if you look into the internals of SM, so they have like, instead of 32, they have now around 64 compute nodes. And also they have a dedicated tensor core units. So the tensor core units are basically for performing vector matrix multiplication. So as we've seen before, the DNNs has most of the computations from the vector matrix or matrix, right? So we can easily upload them to the tensor cores. And they also have a SFUs, which stands for special function units, which can be used to perform the nonlinear function and stuff. So compared to 2009, they improved and tuned the architecture a lot for the neural network and improved the performance in general as well. So that's why the GPUs are like really offering a lot of compute performance. So this one offers like 125 teraflops per second, which is quite a lot. Okay, so the little bit in terms of the tensor core. So what it basically does is the matrix multiplication and then addition at the end. So the addition is kind of optional as well, and they operate in 8-bit or 4-bit mode. So to use this, you can just use an intrinsics or assembly programming, which should not be that problem, I think. Now I think the recent one is like released sometime back, and that one, they already increased the size of this matrix they support, and they also have a support for high precision and low precisions as well. So that is actually quite nice. Okay. Right, so one of the main thing we have to consider when using the GPU is the offloading time. So if you have a CPU, you just have a global memory or the RAM where you can put all your data and you can trigger the operations. But if you have a GPU, when you want to trigger the GPU, you first have to offload your data to GPU, right? So which means like you have to copy your data from DRAM to the GPU memory, and you have to trigger the GPU will execute something and triggers the CPU again. And then you have to copy the data back from GPU to the main memory. So this one has quite a lot of data movements, right? So we can't really just use the GPU. So if you want to use the GPU, you have to use the CPUs as well. So in this figure, basically, kind of shows like what kind of energy we spend on the CPUs and GPUs when we do an offloading. So for example, if the K20 is, I think the GPU, K20 TX are the GPU versions, and Caffe, Torch, and TS are like, the libraries we use to implement the deep DNNs. So as you can see, for K20 Caffe, around 50% is on the GPU, and remaining is actually spent on the CPU in terms of energy. And so this is normalized to just CPU only execution. So if you just run the entire thing on CPU, we get 1. So basically, if we offload it to GPU, we gain performance of like around 35 or 25 to 30% on this one, and up to like 60% on the, depends on the library. So as you can see here, okay, so K20 has an good offloading. Well, the K20 is a bit lower version of GPU. So when we use them, the power is not that big, but the TX or Titan X are really high-end GPUs. So the power actually spikes here. So, but still, the overall runtime actually goes down. So if you are interested in runtime, then the recent GPUs are quite better. And if you're interested in power, then you have to kind of do the, you just have to calculate yourself by combining these two powers and say how much time it takes as well. Okay, so in summary, if you are choosing a GPU, you have to be a bit careful about the offloading time and stuff as well. Okay, so let's see if we have some questions now. Oh, wait, okay. How to decide number of neurons in each layer? You cannot really decide it, so it depends on your application. So you just have to do one trial and error model. So when you train your model, you can try it with the smallest number of neurons and try to check your accuracy. And if your accuracy is good, then you can leave it. But if your accuracy is not good, then you have to increase the neurons and redo the training. So in summary, the accuracy kind of relates to neurons, right? So if you have more neurons, you get more accurate network or good performance in the inference. That's the main thing. Okay, I hope that answers the question. And anything else? Okay. Again, guys, like, if I go too fast or if you want something specific, just let me know. Okay, so this is quite nice. So I previously talked, okay, you guys might be already training a network or using them. So normally you guys train the network on a TensorFlow or something higher level software, and then you just say, okay, implement in the CPU, and that there's some magic program will happen, and that will produce a program for your CPU. But internally, what it really happens is that when you do on TensorFlow, it actually calls the intermediate library. So the intermediate library is the one who actually implements the neural network, which basically it implements the nested for loop. So the TensorFlow, it just gives an abstraction to use that for loop. So the intermediate libraries, there are quite a lot of libraries. So the MKL, DNN, BLAST, blah, blah, blah stuff. So exactly which library is best for your use case is highly depends on your target and what kind of network you are training and this kind of stuff. So a little bit closer look. So let's say if you're designing a network in the TensorFlow, so what you normally do is you just specify that you want a convolution layer with 32 layers of with kernel size 3x3 and blah, blah, blah stuff. And you want to say ReLU is your activation function. So this is really nice because we abstract all the complexities in the TensorFlow. But what happens is when you compile the code, this one calls links the intermediate library. So in this case, I used an ARM neural network library, so which basically takes this to the call and kind of implements into a really low-level program, or in LLM, it's an IR code. So I just want to give an example. So I didn't find a proper one, so I just put something here. So don't look into the exact things. So basically what happens is this gets expanded inside ARM neural network library, and this is passed to the compiler, and then compiler does the optimization. So as we've seen before, so it's just a kind of a for loop, right? So let's say if you have one like an 8-core processor and if you have a 12-core processor, the library can detect the target. So it can already detect like whether your hardware is 4-core or 8-core. And based on the number of cores, it can parallelize the for loops. So basically what it means that the library has more knowledge about the hardware, so it can do more optimizations on the for loop. That's how they get major performance out of it. Okay, so yeah, another interesting thing. So okay, since no one is really interacting much, so I just want to post this question and see like how we managed so far. So here we have a graph, which in the x-axis we have an libraries, and on the y-axis we have an energy efficiency for one inference, which is for one image. So the blue ones are actually CPU energy, and green ones are DRAM energy. So as you can see, we in this entire performance is just from just for implementing a simple CNN network. And we run, basically we take a network and we try to run on Xeron E5 with different libraries. So as you can see, we have a different performance here, right? In terms of the energy and as well as average power we can discard it, but in terms of energy. My question is like, why do you think there is a difference in performance for different libraries, even though we implement the same network on the same processor? Yeah, you can just type in chat or you can just unmute and speak as well. Okay. Is the question clear or? Okay. Probably no one is listening. They just, I guess, but yeah, I hope not. Okay. Okay, so that is basically because like each library is implemented by a specific vendor. So, I mean, so for example, MKL is highly tuned by Intel, and OpenMP also they kind of support it. So when the vendor tunes the library well, then they behave good on that particular platform. So OpenBLAS is actually mainly for GPU and stuff. So that's why like we are using kind of a GPU optimized library for CPUs. It still gives you better performance, but not really. So when you choose a library, you have to be really careful about the target. So if you try to link it with a long library, then the performance would be really poor. So yeah, this is more high level anyway, but should be fine. Okay.
Excuse me, sir.
Yeah.
Sir, I have a question. Actually, this is other than your question.
Yeah, sure. Go on.
Sir, how we can decide the configuration for a project? I mean, configuration of GPUs with respect to a project, which includes deep neural networks and with several GBs of data.
Okay, so it depends on how much money you have, basically. So
Okay.
I mean, if you go for a super duper GPU, then of course you can train really quickly and use it. And you can also train it with really small
If
computers as
time
well.
is not a constraint, sir, then how we can go for it?
Sorry, what was the question?
Time is not a constraint that I can wait for a day.
Oh, okay, but it also depends on how big your network is. So I would recommend, actually, you don't have to buy anything. You can just use the one which are available online. So there is something called Collab.
There are n number of platforms, sir, and which is very confusing. That is
Okay.
whether we need
Right.
to with AWS or Azure. So basically, I was confused there because different configurations with different spending is also there.
Yes. Okay, so in this case, I would highly recommend to go for free ones, which is Google Colab. So there is something called, do you know about it?
I'm actually using it since last 3 years, and basically the problem is I need to keep my laptop on the whole time whenever I'm running it.
Yeah.
The collab, and that means I could not shut down my session and
Okay.
go for other stuff. That is the issue with collab, I guess.
Okay, yeah, that's true. But okay, there are some things we can do. But okay, so this is like really specific question. So maybe we can discuss at the end of the presentation,
Sure,
if you don't mind.
No issue, sir.
Okay.
I'll contact
And sorry, your name?
Vipa. It's Vipa.
Deepa, okay, yeah, okay, cool. We'll get back to you at the end then.
Thank you so much,
Okay,
sir.
yeah, thanks for speaking up. And any other questions?
Thank you, sir.
Cheers. Okay, great. So I think we still have like 30 minutes, right? If I'm right. Oh, no, okay, probably 20 minutes or something. Okay, so I was planning to give a break, but I mean, maybe we can continue. We don't have a lot of discussions in which should be fine, I think. Okay, so next is more specialized hardware, so which is like having a dedicated hardware for a neural network or the general deep learning. So as we've seen before, like the main computation is actually from the matrix multiplication, right? So if you design an accelerator which can do this matrix multiplication effectively, then we are already there almost. So that's what most of the accelerators are based on, but there are more to it, but that's the basic core model. Okay, so most of the accelerators are spatial architectures because of the two reasons. The first is like, okay, so in this case, you are actually taking one vector and you are multiplying with each column, but you are producing one output. But if you take one vector and if you try to do the multiply with all the columns, then you get the entire row output row in just single go, right? Which means more parallelism. But when you do multiply, what you do is you take first value and you multiply with the first column, so first row, and then you sum it with the next multiplication and just go on. So basically, we multiply as a vector and then we sum over the columns, right? So if you have an architecture something similar where you can just put weights, then if you pass an input vector, then the input vector kind of shared to all the columns. So you can perform all the multiplications in parallel, and in the row wise, you can do an accumulation through different ALUs. So basically, whenever you pass one vector, you can produce one complete row at the output, right? So this is spatial because like we organize the computation nodes to match the input vector or the computations. So in the ALU, most of the accelerators, they use different strategy for register file control and what kind of operations it can perform and stuff. So this is not really that important. Okay, so one of the popular example that I mentioned is like TPU, and yeah, the first one is the on 2016, and that is basically they put it on the cloud, so like the one on the right, so you can access through Collab, and yeah, you can use it for free. Okay, internally what they have is the matrix multiply unit, which basically has an it can perform 64K operations per cycle. So it's a 256 cross 256 matrix multiplication array. So you can put 256 cross 256 weight, and you pass 256 inputs of basically one vector of 256, and you produce an output of 256. So this is actually quite a lot of computation, but the computation alone is not good. So I mean, we also have a really intensive memory use. So to have a memory use, they have different levels of memory hierarchies. So they have DDR3, local buffers, and yeah, they have some other extra structures as well. So what they really did is they understood the actual challenges and what is really needed for the DNN, and they tried to create a specialized unit to handle that computation, which is actually, the performance is really impressive as well. So how it works, yeah, as I mentioned before, so you store the weights and you pass an input vector, and this is shared to all the units, and they actually get weighted some over here, and we can do accumulation over here as well. Okay, so this example basically tries to calculate the same thing. So this is your input, and this is your kind of weight matrix. So what you do is, yeah, I mean, you can't really pass a vector and get it, because like for each stage you have a single cycle latency. So what you do is you pass and shifted input. So in this case, ideally what you want is you want to perform, multiply x with w and produce this result. So x11 is multiplied with w12, and yeah, this thing and robot. So this is kind of trivial example, I believe. So what you do is you shift your input and you pass your input one by one. So in the first stage, what you do is you pass the first input, then you get multiplied, and this multiplied output will go to the next one. So basically, like what you do is in the next cycle, you pass the x21 and x12, and this will get multiplied with the w11 and w12, and this results we previously multiplied gets shifted, and then it goes on. Okay, I will share the slides later. You can just kind of see the animation. So yeah, basically it means like we are just perform. Yeah, once we load after this cycle, whenever we pass a new input, we get a full output. So we have a setup latency and loading latency, but it's not that important. But because like we have a lot of computation, so that can be hidden completely. Okay, so in terms of performance, here we have a roofline model. Well, basically, just done plot to show that what is its peak performance and kind of an weight reuse. So weight reuse, like once you read from memory, how many operations you can perform on the weight, something like that. So as you can see, that the roof lines are the interesting ones. So the blue ones are actually for the TPU. So as you can see, the performance it can offer is massive, like up to 100 teraops per second. And for GPU, it's actually better than the CPUs, which is yellow. But yeah, as I said before, so the CPUs and GPUs have some generality. So that always restricts the performance. Sorry, one sec. Oh, yeah, okay, sorry. So basically that restricts the performance. And if you want to offload it to CPU or GPU, so they offer, their peak performance is quite large, but if you practically try to implement it, so their performance is always below this line. So this line is basically the maximum we can get out of the system. So this is for i9 core with, Henswell with 19 core CPU, and GPUs for something else as well. So yeah, that gives an idea. And yeah, the recent ones are like they have a different versions, V2 and V3. So they try to improve the array size and more precision and stuff. We don't have to look into it. Okay, so we have like 15 minutes, I believe. Research outlook, yeah, I just give a quick summary because, yeah, I mean, if you go in detail, then it takes forever. Right, so the main problem in most of the architectures of CPU, GPU, DSPs they are based on one-human architecture, which means like you will have your weights in the memory, and whenever you do a computation, you try to move weights from memory to the control unit, perform your computation, and write it back to the memory. So this data movement costs a lot in the hardware, especially for the energy efficiency. So if you access your DRAM, the energy budget is quite high. So that's really a bottleneck. So what we try to do is we try to store the weights in the memory and do the computation in the memory itself. Then we can completely eliminate these data movements, right? But how do we do it? Okay, there is a technology called memristors. So memristors are basically like 3 terminal devices. So you can actually kind of store the weights there, and when you pass an input, then it can actually do a computation over the stored weight. So for example, it's like a resistor itself, but it's like a tunable register. So if you have an weight programmed on the register, so the current which passes through this resistor is based on the input current and the resistance value, right? So we get an, just by Ohm's law, we get an final output here, and this output is again goes to this line, and similarly the next one produces the same current. So when at this point, basically this current and this current are combined together. So as you can see here, we are passing a vector, and we store the weights in the resistors or memristors, and this automatically performs the vector matrix multiplication. So this is just for 2, but if you scale it, we get like a whole array. So you can just pass one input, and everything happens. You just have this input to all the memristors. And similarly, when just with the Ohm's law, when we collect the currents, we get a vector matrix multiplied output. But this one has quite a lot of challenges as well, because like we are performing the computation in analog, so the analog has some its downside, and the DNN is digital, so we need a boundary between analog and digital. So the design of mixed signal is quite complex. So currently, I think the practical available ones are 128 cross 128 array, but still it's in the practical. It's not commercially used. It's just on the research field. So this is the project I'm actually working on. So to design and compiling framework and designing a system level stuff for the memristor-based computation units. Okay, so this is pretty well basic. So we can't really just use the memristor because you still have to compute the normal stuff. So basically what we do is we just put this SIM computing memory unit as an accelerator unit to the entire system. Then the host can perform the general operations, and SIM can perform the vector matrix multiplication. That's the overall idea. Oh, wait, sorry. This is not actually from the ISAC. So this is actually from my paper, which is like last year, I think. But it should be fine. Okay, so in terms of energy efficiency, what we gain is, another thing, important thing that I missed is like this can actually perform the computations in really, really energy efficient way. So that's where we gain a lot of energy. So in digital, you have to wait for the clock, and there are quite some restrictions, but in analog, these memristors are really energy efficient devices. So in terms of energy efficiency, we gain a lot. So in average, like we gain like 10 times, I think. Okay, but yeah, you can look for the figures later as well. Yeah, there are quite a lot of complex architecture as well. So the one here is just with a single tile. So you can put multiple tiles and you can have an interconnect between them. Then you can implement multiple layers with specialist units and stuff. The same as the other story. Okay, this one also let's skip. Right. So any questions on the research outlooks or the previous topics so far? Right. Okay. So let's continue with the conclusion as well. Right. So yeah, as we've seen before, the compute intensity of DNN are quite high. Not just the compute intensity, the memory requirement is also quite high. So the CPUs are good for general applications, but when it comes to DNNs, they are not that efficient. But the recent trends, they are adding new extra units in the CPUs and GPUs to perform the vector matrix operations. So they normally as a coprocessor are kind of an accelerating unit. So that already helps, but still, because of the generality and the control overhead, they are a bit far behind the the ASIC designs. And yeah, again, the energy efficiency is a concern in them. The special purpose architecture, they can reach really, really high energy efficiency, but their flexibility is less. Like, yeah, if you buy a TPU, you can only use it for the matrix multiplication or a DNN inference. You can't use it for any other stuffs. Then it will not be energy efficient anymore. So it's not that interesting for the general ones. And in research, there are quite a lot of topics around it. And yeah, I'm particularly interested in the computed memory, but there are other domains where they were looking into saving the energy efficiency as well. So they even have a digital design where we can perform the computation in the SRAMs. That is actually, yeah. Okay, so, and yeah, this one already covers. Okay, main takeaway is like choose your hardware platforms wisely. So if you choose a wrong platform, well, not just a hardware platform, also a software platform. If you choose a wrong combination, then you will end up paying a lot of money or like spending a lot of power and wasting your time, more importantly. So choose your libraries, hardware, and the network based on what you really need and your use case. Okay, so to come back to our planning, the first slide. So my goal was to give an overview of the deep learning and what are the design challenges and how we can have an understanding from practical point of view. I hope I covered most of the time, but I'm not sure about the last part because I was expecting too much interactions. So yeah, that's fine. Yeah, so I hope this covers everything. And yeah, so if you are interested in something specific or research projects or papers, you can always look into this one. So this is actually our research group site. And CGRNL is actually the architecture that we are currently working on to have an reconfigurable architecture for flexible computations. Yeah, hopefully we will, yeah, this is already published, so you can find that link over in the parser somewhere here. Okay, so this actually concludes my presentation, and I think we have like 10 minutes. So if you have any questions, and I hope you have a lot of questions. So yeah, I'm open for any questions. Okay.
Participants, if you have any questions, you may ask. You can unmute and ask.
Okay. Oh, no question. So either I went really, really fast or I don't know. I can't really say. So
Can you please share your contact details?
yeah, so I think you can just search it, just Kanishkan very well, but yeah, I will send it here as well. I sent it in the chat box. Yeah, should be fine. And yeah, generally, like our group is quite open for collaborations. And if you really have some interesting challenge ideas, so yeah, and competence, yeah, you guys can always reach anyone in the group. And yeah, should be fine. So yeah, okay, thank you. It's my pleasure. Okay, great. Then yeah, I think there is no question, so we can conclude now.
So there are no questions, I think. Thank you, Kanishkan, for accepting our invitation.
It's my pleasure, ma'am.
Thank you.
Okay, so have fun and enjoy the rest of the season, guys. So yeah.
Participants, the link for attendance and feedback is being posted in the chat box. And the link for tomorrow's first session, that is at 10 a.m., is also being posted. So do log in with that link for morning session alone. Thank you.
Okay, right. I believe that was a question from Vidya, I think, for the TPU. Okay, she can reach it in the email. So yeah, thanks a lot. See you. Bye-bye.
Thank you, Kanishkan. Bye.
Bye.